Hi there, and welcome to Raelene Math. In this video, we will see how the slope of a secant line can be used to build or determine the slope of a tangent line. So here we have a curve, a concave down parabola in blue, and we have point A currently located at 0, 0, and point B in purple, which is currently located at 3, 3. We also have the tangent line to the curve, to the blue parabola at point A, and we can see that the red tangent line has a slope of rise 4, run 1, so the slope is 4. Currently, we have a secant line with a slope of 1 because we're rising 3 and running 3, and I can drag this point B anywhere I like. So in particular, if I take point B down here, the purple secant line has a negative slope, which is not a very good approximation to the red tangent slope. I can also see that the slope of the purple secant line is negative 0.23 because I have a delta y over delta x calculator for the given points A and B as they're labeled. So if I start to drag that point B around, for example, to the other x-intercept of the parabola, I have a horizontal line and my slope is 0, if I can get it exactly on the x-intercept. It's close enough. So you might ask, how is the secant slope actually a good approximation? Negative numbers and a value of 0 is not a good approximation to the red slope of 4. Well, it turns out that after a certain point, once the point B, the second point of the secant line, gets close enough, the secant line starts to have a slope that approximates the tangent line. So right now we have a slope at about 2, and we can see that ourselves. If we rise from point A up 4 over 2, the slope is 2. If B keeps moving towards point A, right now the slope of that the secant line in purple is rise 3, run 1. And so the slopes are getting closer and closer. Keep your eye over here on the secant slope calculator as I drag the purple point B closer and closer to the point of tangency A. And so now we see the slopes are 3, 3.15, 3.3, 3.5, and so on. The slope of the secant line in purple is getting closer and closer to the red tangent line's slope. We can also see that the purple secant line is getting closer and closer to the red tangent line. And what happens if we actually put B on top of A? For now, we see that the slope of the secant line is 3.95 and B is almost on top of A. If we zoom in a little bit, it's really hard to even see the difference between the purple and the red lines. But as soon as I put point B on top of point A, I just jumped off of it. Look at the secant slope calculator. It's very hard to get right there. If you take a look over here, it says that the slope is undefined. Now that means that the slope value either fails to be a real number, a finite number, or a single value. And so we are going to have to look at limits to see which it is. In fact, what we're doing is imagining that we have a slope through one point, and so the delta y, the change in y is 0, and the change in x is 0. So let's take a look at how we can use calculus to actually determine the tangent slope from the secant slope. So here are a few pictures to summarize. The first secant slope is a slope of 2. The next one is 3.3, which is getting closer to the tangent slope at point A to the curve, which was 4. But when we actually let point B equal point A, be on top of it, we get that the slope is undefined. Now recall that being undefined means that a solution fails to be either a real or finite or single solution. And so in this case we have that the actual solution or slope value is defined because it's defined to be the single finite value of 4. And so when we look at a secant triangle from, say, the second picture, we actually have a delta y of something and a delta x of something. But as point B approaches point A, we actually see that the triangle shrinks and collapses to a single point. So the delta y approaches 0 and the delta x approaches 0. And we're getting that the secant slope is 0 over 0, which is indeterminate. This value will be determined to be 4 because we can see from the graph that the tangent slope actually exists. How we do that involves limits. So the big concept of calculus, of differential calculus, is that as point B approaches point A on a particular type of curve, it has to be continuous and it has to be what we call smooth, that the secant slope through points A and B approaches the tangent slope. And so in limit notation, we express it as m tangent equals the limit as b approaches a of m secant. But the b approaching a isn't specific because point b and point a each have two coordinates. So we specify it by saying the x-coordinate of point b, the second point, approaches the x-coordinate of the point of tangency. And therefore, the secant slope through points a and b approaches the tangent slope at a single point on the curve a. And a is called the point of tangency. We can express that as limits as well. So let's take an example or look at a labeling of a picture where we have a fixed point of tangency. Now I'm using the lowercase a for the fixed x-coordinate. It's a letter as well, it's a variable, but we call it a parameter. And we're going to take point B as being flexible or moving, and so I'm going to give it variable coordinates x, comma, f of x on this graph in blue, which is the y equals f of x function. And so from our big concept then, where we know that the secant slope turns into the tangent slope, in other words, m tangent equals the limit as point B approaching point A of m secant, we can therefore calculate the slope at point A to be the limit as the x-coordinate of point B, namely x, approaches the x-coordinate of point A, which is little a, of the delta y over delta x. And we can calculate the rise and the run because we have the x and the y coordinates of two distinct points because point B is not yet at or on point A. And so we have y2 f of x minus y1 f of a all over x2 minus xa. Now we can label the graph differently. We can still call point A the fixed point with coordinates a comma f of a, but we could actually move h spaces to the right or some delta x, which is variable. And that h or delta x can change, but that gives us a second point B which can move. And so the coordinates of point B will be a plus h for the x-coordinate and f of that x-coordinate for the y-coordinate. Then we can still calculate m tangent. This is the big concept, which says it's the limit as point B moves towards or approaches point A of the secant slope. And therefore, the slope we are interested in is the slope at point A, which is the limit as the x-coordinate of the second point, a plus h, approaches the x-coordinate of the point of tangency, which is a, and we calculate delta y the same way. y2 minus y1, and we calculate delta x the same way, x2 minus x1. Now we see we can simplify the denominator, and similarly we can subtract a. Just like we do with an equal sign, we treat the approaching arrow in the same way, and so we end up getting the limit as x approaches, rather, the limit as h approaches 0 of f of a plus h minus f of a all over h. Now this result looks different to the one that we just saw. However, it's just two different labelings of point B, and it's going to give us the same result either way. Depending on the algebra, we may choose to use this option to come up with the tangent slope at point A, or we may use this option. There's a third possibility that's quite common, and that's that point A is no longer a fixed point because we might want to come up with a tangent slope at some other point on a curve. And if we do that, we need to allow point A to have variable coordinates, and so we tend to call the coordinates of point A of x comma f of x. To generate our second point for the secant line, we go a change of delta x, or h, away from point A, and we come up with the x-coordinate is called x plus h, and the y-coordinate is f of x plus h. Now our big calculus concept says that the tangent slope is equal to the limit as the second point on the secant line approaches the point of tangency, and we take that limit of the secant slope, and therefore the slope at point A for this labeling takes the x-coordinate, x plus h, and approaches x, which means h approaches 0. And the secant slope is calculated by y2, f of x plus h minus f of x, over delta x, which is going to be simply h, because x plus h minus x is just h, which we call delta x. So there are three different ways of calculating the tangent slope. But what's interesting to note is that this is just like working out the limit of a function. What height does a graph approach as x approaches something? In this particular case, this is some function, this whole rational numerator over denominator function is some other function, let's maybe call it g, and it depends in this case on two things, x and h. And we know that if we substitute directly, we are working out a function value, so g of x comma 0 would actually be f of x minus f of x all over 0. And that would give us 0 over 0. And so this is the indeterminacy that we were seeing earlier when point B approaches point A. If we go back and look at the other cases we came up with, if we did a direct substitution again for each of these, if we substitute some function g of a comma h, now a is just a constant number because it's a fixed point. Little a is constant because big A is a fixed point. Then working out g at a comma 0, i.e. substituting h equal to 0, would give us f of a minus f of a, which is 0, over 0. So there's the indeterminacy again. And for the first example that we had, if we take this as some function of, sorry, it's not, we can't use f here actually. This is a good mistake that I made because we're already using f for the graph of the parabola. The bubbled function is no longer the y equals, let's see, this is negative x times x minus 4 function. That's not the same as what's inside here, so we need to give it a new name. So I want to call it g. And so the g function depends on x and a. Well, a is a constant again because we have a fixed point, capital A. But anyway, if we were to substitute x as a, then we are going to get f of a minus f of a, which is 0, over a minus a, which is 0. So in each of these three cases, direct substitution into the expression that we take the limit of, namely the secant slope expression, which is this g function I keep calling. The secant slope is the g function. Then direct substitution gives us indeterminate. And as we know, indeterminate may be a value that means the limit exists, or it may not. And so we have to determine it. So stay tuned. In the next video, I will run through some specific examples of how we determine it. Thanks for checking out Raelene Math.